Hello everybody, let us continue our discussion on canonical transformations. We started by writing down the canonical Lagrangian and the canonical action. So in terms of the canonical Lagrangian, the action looks like this, and if I write down the Lagrangian, it looks like pi dqi minus h dt. And then we said that we'll do a transformation, change PQs to capital P's and capital Q's, say, but the canonical action will remain invariant. Such that the equations of motion remains invariant. That was the condition for canonical transformation, and we also imposed the case that h as a function of this, I should write qi pi, is same as and you see that we considered the cases where Hamiltonian is independent of time. We'll continue to do so in most of the lecture today, and I will tell you what happens if it is not independent of time, and if you wish you can formulate things where it is not independent of time. Then we wrote down for a general case, this essentially means that pi dqi minus capital Pi d capital Qi, this is equals ds, where s is a function of the old coordinates, old q's, half of the coordinates if you write in terms of the Hamiltonian, the canonical action, and the new coordinates or half of the new coordinates, capital Qi. This has to be true because the difference between pi dqi minus capital Pi d capital Qi not need to be 0 because their integral has to vanish. So this ds means that it has to be equals to the total differential of something, and this gave rise to the conditions which you get by writing ds. So ds I can write here as del s del qi dqi plus del s del qi d capital Qi, and that gives rise to the fact that this has to be identified with that, tells us that pi is del s del qi, which is some function, let me call it f1 of qi and capital Qi, because you see that s is a function of small and capital Qi's. So if I take a derivative of that, partial derivative of that with one of these variables, it will be a function of those variables only. Similarly, we got that capital Pi is minus del s del Qi, which is just by equating these two terms. And that again you can write as some f2 of again the same things. So I get two equations, two algebraic equation now between p, q, p's and q's, old and new variables, I can in principle solve them and figure out what are the new variables in terms of the old variables. So because of that, we realize that this S is actually, if it's given, I can generate the transformation. So this we call the generating function. And this particular form of S, which is a function of small and capital Q's, I call this G0 because it is the fundamental generating function. 0 stands for that. I will call this G0, small qi, capital Qi. Okay. So this is what we discussed last time. So let us proceed, and let us first take away one case where what if the Hamiltonians are independent of are dependent of time explicitly. Then the Hamiltonians we cannot assume to be the same for the two cases. So if the Hamiltonian so in that case, what I have to do is I have to write the canonical action as like pi qi dot minus h. Now it's a function of qi, pi, and t. And this should be same as if the transformation is canonical. But now there's a different function, so let me write this explicitly as h prime. And this is a different function of its variables. The time in classical mechanics remains the same, so it's the same time. So now if I do the same thing as I did here, the way I wrote down this is identified the terms in the two parts of the action which are not same, and wrote that in the left hand side. The excess I wrote as d capital S, which is the total differential. I do the same thing over here. So I say that, okay, so this is pi qi dot minus now capital pi capital qi dot dt or let me write it as without dt, it's alright. And then I can add to it h prime minus h. And this entire thing now has to be a differential. I still call that s. But now s is a function, has to be a function of all these q's. And now it can be also a function of time, because the Hamiltonians are function of time. You see, why s has to be a function of both the q's? Well, I wrote the differential in this side, but if you think, you can actually add a differential here and add a differential here. If I add the differential on the left hand side, it has to be function of the variables in the left hand side. If I add the differential in the right hand side, it has to be function of variables in the right hand side. So because of that, I put both the variables in the left and the right hand side in my S. Okay, so that is the reason why I kept this as function of both the variables. Okay, so now let's see what happens with this S. So I will do the exact same thing as I did before. I will write ds in terms of its partials. So by the way, this has to be ds dt. Here I have kept the time derivatives. Now what is ds dt? Well, it is del s del qi dqi dt, which is qi dot, plus del s del capital qi the capital qi dt, which is capital qi dot, and plus del s del t, and that's all, right? So you realize that if s is a function of time, then my Hamiltonians does change. So the canonical transformation equations that I get, I should keep this equals ds dt over here, and now I get the following relations. I get, just as before, pi equals del s del qi. I get capital Pi equals minus del s del capital Qi. And additionally, if since s has explicit time dependence, that is given by the difference in the two Hamiltonians. So if s does not have an explicit time dependence, the differences in the Hamiltonian is 0. That's what we got earlier. So if the differences in the Hamiltonian is 0, then your generating function not need to have an explicit time dependence. Okay, so now let us look at certain transformations. What we will do is, in the rest of the discussion, we will not keep the time dependence. You can put the time dependence whenever you want, just the way we have been done here. Okay, it's absolutely trivial. So remember that we have discussed, we have defined our generating function as qi, function of qi and capital Qi. And let's take one example. So this is the case 1. Let us ask the question that in this particular case, we got a generating function, which we said the fundamental generating function is a function of the old code, old q's and the new q's. It has to be always a function. If there is anything which generates a transformation, canonical transformation, it has to be a function of something from the old and something from the new. So that is to be a property of the generating function. Let me write it here. At least it may have more, but at least it should have one from the old and one from the new. Okay. So with that, I don't need this anymore. Okay. So with that, let us take an example and see what type of transformation it gives rise to. So say G0 is, what is the simplest thing that you can think of? Q times capital Q. Okay. And that will be our theme. We will consider a few more cases, but always we'll stick to that particular type of generating function. Okay. Small q times capital Q. Fine. So this is my generating function. Now let us ask the question that what is the transformation this generates? Remember that in the old coordinates, I have Q and P. I'm just writing it this way. In the new, after the transformation, I have capital Q and capital P. So what is capital Q and capital P in terms of the small q and small p? So let us work it out here. We know that small p is del G0. Remember, my S and G0 are the same thing, del Q. So if I do del Q in G0, what I get is capital Q, right? So capital Q will nothing but be the small p. So the capital Q will be small p. So that's what I write for the capital Q here. What is the other thing giving me? It's giving me that capital P will be minus of del S del capital Q, which is, if I do del G0 del capital Q, I get a small q. So del G0 del capital Q, I'll get a small q, but I had this minus sign, so I get minus small q. So capital P, or let me give the full arrow, is minus small q. Okay. So let's have some fun. So we usually plot q this way and p this way, and if we want to preserve that, let's see how the new system looks like. The new system is capital Q and capital P. Now capital Q is nothing but P. So this is P. And capital P is nothing but minus Q. So this is minus Q. So QP has become Q, so this has come here, and minus Q has become P, so minus Q is this line that has gone there. So this is a clockwise rotation. This essentially is a clockwise rotation by pi by 2, 90 degrees. Right? So if I take this QP, I rotate it by clockwise, then this P comes here, which is along capital Q, and minus Q comes there, which is along capital P. And that's what has happened. Nice. Okay. So you see that as we are talking about here some times ago, that I can write algebraic equations between P's and Q's, and I can solve them to get the new variables in terms of the old variables. That is exactly what we have done here for a very simple trivial calculation. Because I can only do very simple calculations, all the complicated ones will be left for you in your assignments and exams. Okay, so that is case 1. Let's say that I don't want my generating function to depend on small q and capital Q. I may want to say it depends on small q and capital P. So I want a generating function where I have a new generating function, let's call it G2, and it depends on say small q and capital P. And I am just carrying over only one coordinate here, so it should, you can write qi and small qi and capital Qi, there is no harm in that. I'm just writing it, or let's put back all the coordinates. It's not very time consuming. And this I should be able to get from my G0. Remember, that is a function of these two variables. And in G0, that capital Q is replaced by capital P. So I just add to it some alpha, which I don't know what it is. This I don't know at this stage. Times Pi Qi. Okay. My hope is that I should get some alpha such that this works out. All right. So now let's see what was my equation before. My equation, and there is no time dependency here, remember. So my equation is pi dqi minus capital Pi d capital Qi. This is equals to d of g0, right? So that we know that it is equals to d of g0, and d of g0 is now d of g2 minus d of this pi dq pi qi. So d of g2 is, so this is d of g2 minus d of alpha pi qi. So what is d of g2? So let's now work it out here. It is del g2 del qi plus del g2 del capital Pi minus alpha Pi dqi minus alpha qi dpi. Okay. Identify the differentials in the either side. So first thing we realize is that this term is same. Is this coefficients? It has dq d capital Qi here. This also has d capital Qi here, which essentially means that alpha, if this 2 has to be equals, alpha has to be equals to 1. If alpha is 1, then this gets cancelled out with this, and this thing is minus alpha, it becomes minus 1. Okay. Now what else can I do? I forgot to put dqi here and dpi here. So I get to compare now the terms which are having dqi. There's no dot. Sorry for that dot. So this is equals to that, which is pi is equals to del g2 del qi. This is exactly what I had before. But now the new thing that I get is that this is equals to that, which means now I get to write capital Qi now in terms of dg's. Okay, just by changing the form of g0, that's what exactly I have done here, I get a new set of relations, and sometimes these are useful. And let us again take the most trivial example for g2. We take g2 equals small q times capital P, exactly what I did before. Because it's a function of q and p, I just take the trivial example of this. And remember that what I have is that I have my old coordinates, q's and p's. I have only one of them for the time being, which are transferred to the new coordinates, which are capital Q and capital P. These are my new ones. And I want to write down news in terms of the olds using these relations for this particular G2. So what do I get for this G2? I get small pi is del G2 del Q, which is P. So small p remains as it is. And I get Q equals minus of del G2 del capital P. So this is minus Q. So Q becomes minus Q and P is P. And let us do that fun again to draw these two coordinates. So I have Q here, P here, and capital Q here, P here. So capital Q is minus Q, so this has come here. I am sorry, you see that this term was minus 1, so I should have got this is equals to, this is plus sign. So capital Q is also plus Q. Okay, so that was a mistake which now we have corrected. So I should now have to remove this. So it's a boring transformation. So this is small q is equals to small q, capital P is okay, there is no transformation. This is identity transformation. So this generating function gives us an identity transformation. All right. Let us. So what we had done here is we replace this capital Q by capital P. Let us do the reverse now. Let us keep capital Q as it is and replace the small q by small p. Okay. So let us try to do that and see what type of transformation properties that gives us. So that's my case 3. So this I call G3. Now this will be a function of P and Q. And if you wish, we'll keep all the coordinates. And let's see how do we get it from G0. G0 is a function of small qi and capital Qi. And again I add alpha times the terms which have what has replaced what. So this is Qi and Pi. And you know the drill now. So I write down Pi dqi minus capital Pi d capital Qi equals dg0, which is now dg3 minus alpha d of Qi Pi. And if I work out the right hand side, I get d del g3 del Pi dpi minus alpha Qi dpi minus alpha Pi dqi. And now you realize that this term has to be same as this term. So now my alpha has to be minus 1. If alpha is minus 1, this term and this term goes away. And this just becomes plus 1. Right? So what do I get once I compare now things? You see that I can compare, I can compare this with this, and I can compare this with this. So once I do those, what I get are these. Del G3 del small pi, sorry, and I get Qi equals, this also minus, because there's a plus sign here and both of them are in the same side, so they should add up to 0. So Qi equals del G3 minus del G3 del Pi. Nice. So that is the new set of transformation rules. And now let us again see for the most trivial case of G3, which is a function of P, small p and capital Q, small p and capital Q. So I'll just take this example. I will see this example in most of the books because this is the most simplest thing that you can think of that will come to your head when you look at this example. So this is the old. Goes to the new, which is capital Q, capital P. And for these, let us calculate here. Capital P is going to be minus del G3 del Qi, which is minus small p. And small q is minus capital Q. So this is just minus p. This is just minus q. And if you do the fun of looking at it geometrically, you see that this is my q and p originally, and later this becomes capital Q and capital P. But capital Q is minus q and capital P is minus p. So whatever was here, minus p, has come there, and whatever was here, minus q, has come there. So this is a clockwise rotation by 180 degree or pi. Nice. So what all we have done so far, we have replaced small q ones here, keeping the capital Q fixed. We have replaced capital Q ones, keeping the small p fixed, and the original thing has q and small q and capital Q. Now the only thing that is left to do is that you have G4, which is small q replaced by small p and capital Q replaced by capital P. Okay, and that again you will write as always, and these are I in terms of Qi this. And now you know that which will have what sign. For one replacement I need this with alpha negative, so I'll just put minus small qi pi here. And for the other replacement, I will need alpha positive, and I will need to put plus capital P, capital Q. So plus capital Pi, capital Qi. Okay. So I leave for you to figure out two things here. So this is your homework now. Figure out the transformation rules. In terms of G4. Take the example of the trivial example. Okay, let's in the line of what we have been doing so far, and also see geometrical interpretation. Okay, so this is your homework. So let us see what we have done so far. We were recapitulating in the beginning, where we said that uh, for a canonical transformation, it's a transformation of all the Hamiltonian coordinates such that the canonical equation remains form invariant, and that we started with the canonical action and figured out in the case where the generating function is not explicitly dependent on time how this look like. And then for one set we looked at once what if the generating function has a time dependence, and the explicit time dependence of the generating function comes here in the difference in the Hamiltonian. In that case, they will be different. Then we looked at different examples of generating functions when they are functions of several pairs of the old and the new coordinates. So old position, new position, old position, new momentum, old momentum, new position, and finally your homework was old momentum, new momentum. Okay, this is what we have done so far. But let us ask one question at the end, and that will, once we answer that, that will finish our discussion on canonical transformation today and for this course. Is that how do I know that a transformation is canonical? Say I have got, so let us ask this question. How do I know? How do I know what is that we are saying is, say initially I had a set of QIs and PIs, and I said okay, so I give you a transformation where I tell you that I have new QIs and they are function of all the old Qs and Ps, and new PIs which are again functions of all the old Qs and Ps. But how do I know? Is it canonical? Now, it turns out there is a very nice way to answer this question, and that's what we'll discuss today. Discuss right now. Remember, we said that the volume in the phase space is always conserved. What does it mean? It means that if I have, say, n is the degree of freedom, so if I have all these Q's and all these P's, and I have n of them, so I write it this way. This is a volume element in the phase space. This must be equals to the same in the transform space. It will preserve the volume. But you know that in general, so this is property of phase space. In general, for any such transformation between two set of coordinates, the volume element changes this way, where J is called the Jacobian of transformation. And the Jacobian of transformation, so let me take an example. Let me write for n equals to 1, you can generalize okay. It may not be so trivial, but it can be done. So I'll do the easiest thing, which is the case of dq dp n equals to 1, so I have only 1, equals j d capital Q d capital P, and canonical transformation means which implies j equals unity. Now I did not write down j earlier, so j is called the Jacobian of transformation. Can be written in either side, but what we have written here is essentially determinant of the matrix del q del q del q del p del p del q del p del p. Okay, it is the determinant of this matrix. What is the determinant? So let's see. So our condition is j equals to 1 for the canonical transformation. This implies this determinant equals to 1. So let's calculate the determinant. The determinant is del q by del p, two terms in the diagonal minus multiplication of the off diagonal terms del q del p times del p del q, and this has to be equals to 1. This is nothing but the Poisson bracket. So this is q p Poisson bracket in terms of the old qp, that is equals to 1. So that is the condition for canonical transformation. Condition for so what all I have to do once I'm given a transformation is to check whether the Poisson bracket is 1. Okay. So I request you to read a little bit more about this, and see how you write the same thing when the transformation is not for n equals to 1, but for any arbitrary number of coordinates, arbitrary number of degrees of freedom. Okay, so that completes our discussion on canonical transformation for this course. Next day we will see how this canonical transformation now can be seen as the evolution of the particle trajectory, or how can you get the trajectory out of the canonical transformation.